Okay, in chapter 17, we are talking about energy, and energy changes in chemical reactions, because there is energy changes in every chemical reaction that we do, or the vast majority. Or if there's not an energy change, there's an energy transfer. And so when we're talking about energy, we have to remember what energy is and how we measure energy. So remember there's this relation that we have between kinetic energy and temperature. At the higher temperature we have, remember our particles are moving faster. So if this is temperature right here in our equation, the higher the temperature is, the faster our molecules are moving and the more kinetic energy our sample has. So kinetic energy, remember, is directly proportional to temperature. Temperature is really a measure of the average kinetic energy of a system. So if the temperature drops like it does in this example, well then the kinetic energy goes down and the particles move slower. Okay, so what we are measuring then when we're talking about energy is we're measuring heat. And heat's a word we do have to be a bit careful with because we use heat all the time, kind of just in normal conversations, but it does have a scientific meaning as well. If we're talking about heat, we are talking about a flow of energy from one substance to the other. So it's a transfer. That transfer of energy is called heat. It's a heat flow from one system to another. So say we have these two samples of particles, one at 400 K, the other at 50 K, and we mix them. There would be a heat flow from the hotter to the colder. They'd bump into each other, and they would transfer the energy from the hot system over to the cold system. That is heat. That's a measure of heat flow. And we have a way to measure it. Typically, we'll measure heat flow in a system like this. We'll have some sample. That's our sample. We'll take that sample, say it's heated. So we'll take that sample, say we'll heat it to 100 degrees Celsius. We'll transfer it into what's called a calorimeter. And this really isn't a bomb calorimeter. This is just a picture of a calorimeter, in my opinion. I'll show you a bomb calorimeter later. Anyway, we'll take this sample, say some metal sample. How about iron? Take a sample of iron, heat it up to 100 degrees, put it inside of this insulated chamber. And what's going to happen is it's going to transfer its energy. There's going to be a heat flow. It's going to transfer its heat energy from itself to the water until they come in the So we're going to have a temperature equilibrium that we're going to come to. And if we can measure on this thermometer how much the heat changes, how much the temperature of the water goes up because of the heat from the sample, we can measure how much heat then that piece of iron had. What we know from doing this is that different metals will heat up at different rates, and different metals will heat up the water differently. So notice this observation from doing experiments like this is that gold heats up about 7 times faster than aluminum. So it heats up much, much faster. If you put the same amount of heat into 1 kilogram of both of these samples, the gold is going to heat up faster. Now, what this is called when we're talking about the rates that it heats up, or how much heat energy it has to transfer, we are talking about the specific heat of a material. Specific heats are defined in these terms. So if we're trying to measure this, the amount of heat, that heat is dependent upon a couple things. It is dependent, as we may already understand, it's dependent upon temperature. So if we're thinking about heat and thinking about temperature transfers, you can think of somebody, throwing a can of lukewarm water on you, or a can of boiling water, or a cup of boiling water, and the boiling water obviously is going to burn you more because it has a higher temperature. The other thing that depends on how much heat is the mass of it. So likewise, if we use our boiling water throwing on people example, if we threw maybe a dropper, squeezed a dropper of boiling water at someone, it might burn, but it wouldn't be a really serious injury. Throwing a cup of boiling water or a gallon of boiling water, it's going to burn them more. Why does it burn them more? Well, because there's more heat. There's a lot more heat present because it's a larger sample. So the amount of heat and the potential for heat to be transferred is dependent upon the mass of the sample, how big of a thing we have, what its temperature is, and also something called the specific heat. So that is that rate that things heat up. So like we said in the last slide, that aluminum and gold heat up at different rates. That is a specific heat. And we determine it experimentally by using the calorimeter. So putting the different samples, seeing how much they heat water. The more they can heat water, the more heat they have in them, and their higher specific heat. So let's look at some data. Here's a table of some specific heats. Now notice how they're measured in. They're measured in an energy unit called joules. So that is our Q, which is heat. Sometimes I believe your book uses a small q, but it's Q. I should label that. So Q is heat, its heat, divided by, notice in the units there, its mass, m, in this case, kilograms or grams, so this is joules, and multiplied by the temperature, or the change in temperature. And now notice you can see it uses degrees Celsius or degrees Kelvin because it's a change in temperature. It really doesn't matter. 1 degree change in Celsius is the same as 1 degree change in Kelvin. So typically I'll put down Kelvin. But, occasionally we'll just use our Celsius values as well. Now, one thing I want you to notice while we're looking at these specific heats, again, these are the rates at which they heat up. How much Q, how much heat is required to raise a certain mass, a certain degree, a certain number of degrees. So a lot of times if we look at water, this is liquid water, and I'm going to use these units in calories. It takes 1 calorie of energy to raise 1 gram, 1 degree Celsius. That is water-specific heat. Now notice on this chart, this is much, much higher than any other value. And if we look at these other values, notice as we go down, look at aluminum. That sample on the other slide, aluminum takes about 1/5 the amount of energy to raise. And we know this actually from experience. If you go out on a hot day and you put your hand on the roof of your car, it might be just hot. It might burn you. And one reason is the sun beating down. It heats up aluminum, it heats up iron and steel at a really quick rate. So the ground might not be really hot, but your car might be really hot. You walk across the sand might be really hot. You get down to the water, and what is the water on the beach? The water's so really cold. It could be freezing cold because it takes a ton of energy to heat up water. Water is an amazing substance in every aspect we look at it in chemistry. And one of those aspects that's really amazing about water is its ability to hold heat and how much energy it takes to heat up water and to cool down water. You can also see on this chart the substances we are comparing on the other side. Notice aluminum's here, 0.21. Notice gold right here, 0.03. So it's, like I said on the other side, 7 times more energy to heat up aluminum than to heat up a similar sample of gold. And that really has to do with, again, the electrons and how they can transfer energy between their D shells. And one thing we'd also notice that goes along with that ability to transfer heat also is related to their ability to transfer electricity as well. So it might take it might be a really good transfer of heat, might not take a lot of energy to heat up, and might be really easy to cool that down. And it's also going to be, gold is going to be the much better conductor. It's going to transfer electricity as well as it transfers heat. So our actual calculation is going to look like this. So we have the heat, or notice it's calculated truly, it's the heat, the change in heat. This is the mass. This is the specific heat. And again, this will either determine experimentally via water, or you'll be given a chart similar to this where we plug that value in, and we have the change in temperature. So the change in temperature, by the way, is always the final temperature, T2 minus T1. So we do have to be careful with calculating the change in temperature because sometimes temperatures are going up. And so this will be a positive value. Sometimes temperatures are going to be going down. And so it'll be a negative value. So it's always T2 minus T1. Or we can also write it, if I erase the 2's and 1's, we can also write it T final minus T initial. Sometimes you'll see it that way. So we have the heat, we have the mass, we have the specific heat, which again is specific to each material that we're looking at. It is the rate that it heats up or cools down, and the change in temperature. And all of these can be experimentally derived from our calorimeter. So if we take our calorimeter, we put our bunny in, wait a second. So again, if we take our sample, say we'll take our sample of aluminum, we'll heat it over a flame, or actually, typically what we'll do is we'll heat it in boiling water. We'll leave it in there long enough so we can assume that's at 100 degrees Celsius. We'll take that aluminum out. We'll put it in our calorimeter. We'll notice what the temperature change is in the water. Using the specific heat of water, what we'll be able to do is determine that specific heat of aluminum, the rate at which that aluminum heats up or cools down.